Hello everyone, I am Song Youcheng from Nanjing University. I'm glad to be here to share our work, learning indoor point cloud semantic segmentation from image-level labels. With the development of service robots, augmented reality, and smart home, semantic segmentation on indoor point clouds has become an important research topic. The goal is to divide a given indoor point cloud scene into several regions and assign a semantic label for each region. Deep learning methods have gained much attention and have been intensively studied in recent years. They are data-driven and use multiple nonlinear layers to extract hierarchical features from raw data. With sufficient training data, deep learning methods can automatically mine suitable point features and infer semantic labels, and significantly outperforming traditional methods that require handcrafted features and human power. However, the data-hungry nature of deep learning and the high cost of annotating point-level labels make it difficult to apply semantic segmentation methods to indoor point cloud scenes. Therefore, exploring how to make point cloud segmentation methods less rely on point-level labels is a promising research topic. Weakly supervised learning is an effective approach to reduce the need for data annotation and has been extensively studied in image segmentation tasks. A typical weakly supervised image segmentation mechanism uses image-level class labels instead of pixel-level semantic labels. Firstly, a multi-label image classifier is trained with image-level labels to predict which object classes appear in the image. Then, the activation response of the last feature layer for each class is extracted, which is called CAM, short for Class Activation Map. CAMs denote descriptive image regions used by the classifier to identify object classes and can provide semantic cues for image segmentation. NPRM extended CAM to point clouds and used subcloud level labels as weak supervision. They trained a multi-label classifier for subsampled point clouds and extracted CAMs. Although NPRM introduced an attention module in the classifier to preserve boundaries, the CAMs still provide only core semantic regions. Moreover, CAM-based methods perform well only in discriminative classes, while indoor point clouds have some common classes, such as floor, wall, and ceiling. These classes appear in almost all samples, and it is difficult for CAMs to learn effective region information from these class labels by a multi-label classifier. Here is a brief overview of our method. Firstly, we uniformly sample views in each indoor space and render point clouds into images. Secondly, we annotate image-level labels for each rendered image and train a weakly supervised image segmentation network. Then, we reproject the image segmentation predictions to the original point clouds and generate point-level pseudo-labels. Finally, we retrain a point cloud segmentation network and use it for the testing. The main objective of the rendering phase is to construct a mapping from pixels to 3D points. We divide the imaging plane into pixel grids based on the sampled camera parameters, and project 3D points into pixel grids. We select the closest point to the camera in each pixel grid to construct a pixel-to-point mapping. Then, fill in each pixel with the color of its mapped point to generate the RGB rendering result. To preserve more geometric information, we render the depth image and normal image in the same way. Finally, the RGB, depth, and normal images are combined to a 7-channel feature-rich image as our training image. In the image segmentation step, we use an existing weakly supervised method, IRNet. We train a multi-label classifier with the image-level labels and extract CAMs. Then, collect interpixel relations from CAMs and train the IRNet for predicting object displacement fields and class boundary maps, which are used for refining segmentation boundaries. In this stage of training, we combine the wall, floor, and ceiling classes as a unified background class. Because CAM-based methods cannot produce good results on these non-discriminative classes. In the reprojecting step, we convert image segmentation results into sparse point cloud pseudo-labels based on the pixel-to-point mapping acquired at rendering step. The raw point cloud is over-segmented into patches. We consider that all points within a patch should have the same label. The sparse pseudo-labels vote for their patches and generate point-level pseudo-labels. We also measure the reliability of each patch depending on its consistency and number of votes it received. For patches voted as background, they are subdivided into ceiling, wall, or floor depending on their height and normal direction. Finally, we retrain a point cloud segmentation network supervising with the generated point-level pseudo-labels. Here kbconv is used as our point cloud segmentation network. The original cross-entropy loss is modified to introduce reliability weight for each point. Retraining has two advantages. Firstly, some noise in the pseudo-labels can be filtered out by utilizing the fitting ability of deep neural networks and large-scale training data. Secondly, only the point cloud segmentation network is needed for the final prediction of new point clouds. Here shows some example results of our method and our similar work, NPRM. Comparing to NPRM, our method has better object boundaries, especially the boundaries between the objects and background classes. This advantage benefits from our teamed voting and parallel-based background discrimination strategies. Here shows the difference of weak labels between our method and NPRM. NPRM uses subcloud level labels, and the average time for labeling a scene is about 3 minutes, while our method uses image level labels, and the average time for labeling a scene is less than 2 minutes. The statistical results in the table tell that our method uses cheaper labels while still achieving better segmentation performance. Thank you for your attention.